Okay, so once again, good evening and welcome back to the online interactive lecture series, which have been being organized by the INO project for now. This is the week of 16, so last 15 weeks. Today, again, we have Professor Matthew Szydagis. We already heard him the other day on him talking on the dual phase xenon based TPCs. He is from the University of Albany, the State University of New York. Today is going to talk on seeking dark matter at GeV scales with the supercooled water. So that is the title of his talk. Matthew received his BA, MS, and PhD from the University of Chicago in 2005, 2006, and 2011, respectively, and then continued to work in physics as a postdoctoral scholar at the University of California, Davis. That was from 2010 to 14. Since then, he has been an assistant professor at the University of Albany, Department of Physics, where he is right now, pursuing experimental particle astrophysics, in particular, the direct laboratory detection of dark matter WIMPs. WIMPs stand for weakly interactive massive particles, underground, and general detector development for rare event searches. He works on the LUX, which stands for Large Underground Xenon experiment, and LZ, liquid xenon-based experiments, and he's the developer. So he actually talked about both of these experiments last time. And he's the developer of the NEST. NEST stands for Noble Element Simulation Technique software, about which he briefly talked. We didn't have him speaking at full length on this. And today's talk, the subject of today's talk, that is snowball chamber supercooled water technology, which is useful for both dark matter as well as neutrino physics projects. So this is his brief profile. And since we already heard him once, now we can all look forward to another exciting talk today from Matthew. Matthew, is all over to you.
Thank you. Thank you for that wonderful introduction. Thank you again for the invitation to speak again to you today. So today I'm going to be talking to you about a completely different complementary technology from last time I spoke about noble elements. Today I'm going to be talking about supercooled liquids. And this is work that I've been doing with my collaborator and colleague, Professor Cecilia Levy, also at the University of Albany, Department of Physics. And we're also, as I'll mention later in my talk, building collaboration outside the university as well, across different institutions. So first I want to start by talking about what is supercooling, because that's more chemistry than it is physics. But of course, in particle physics, a lot of our detector technologies rely on some form of condensed matter physics or chemistry. So supercooling is when a liquid is cooled below its normal freezing point, but it doesn't freeze. And this is not the same thing as adding an impurity that changes the freezing point, like salting the sidewalk in the wintertime. So this is metastability. And this is where the liquid is actually very pure. And so this requires high purity and a clean, smooth container, just like with the opposite phenomenon known as superheating, a heating above the boiling point. So freezing occurs when the liquid finds a nucleation site or is otherwise disturbed. So the nucleation can also be triggered by acoustic vibration, also by electric fields intentionally. And it's difficult to process to stop once it starts. It snowballs. The process is highly exothermic. So here is a phase diagram of water. Other elements are similar or different, or elements, compounds, different substances. And so what we're talking about here is going across the solid liquid border, which is at 0 degrees Celsius for many different pressures. So what's interesting about water is the phase transition is from solid liquids nearly a vertical line here. So we're moving across the solid liquid border, but we're going from liquid to solid, but not while crossing into this region of the phase diagram, still remaining liquid. So this is similar to superheating, which is used in bubble chambers that operates across this border, liquid vapor, where you go from liquid to vapor, but you don't actually trigger the vapor transition immediately. So as you see in this cartoon here in the lower right, what happens is you take your liquid like water, you go below the freezing point. This is the supercooled stage. When it does actually freeze, the temperature rockets up towards the freezing point. And so this is what I mean by the exothermic spike. So there is a large release of energy as the entropy decreases of your liquid as it's organized into a crystal, into a more ordered state. And in order to do so, it releases its thermal energy to the surrounding environment. So it seems counterintuitive that freezing heats something up, but actually the supercooled process results in an incredible increase in temperature at the moment of supercool. The material attempts to heat all the way up back to the freezing point. The smaller samples are easier to cool, so the minimum temperature you can achieve is easier if you have a smaller sample. And particle physics, this is a phase transition that has not been explored as much as superheating or supersaturation done in the bubble chamber or in the Wilson cloud chamber. Both technologies that were used for many decades in particle physics, many discoveries made with them. So there are many challenges using supercooled water. So this has been done before. I thought that, we had discovered this at University of Albany. We had rediscovered this. This was done first. Actually, it turns out all the way back in 1909 in France. And then the Russians were looking at it. And then most recently, before our publication on this, the most recent thing we can find is actually from NC Varshnaya at Department of Physics at the University of Roorkee in India, is actually the most recent work we have found on using supercooled water as a particle detector. So the last papers that we have found in existence on this technology were in Nature magazine 1969 and 1971 by Varshnaya. And since then it's been quiet, and that makes sense because there are technical challenges that we have to overcome in order to make this a reasonable, practical particle detector. Now, to be clear, supercooled water by itself is an incredibly huge field of research. There are hundreds of papers, thousands of papers on it. So what I mean that nothing's been written since 1971, I mean specifically regarding use of supercooled water to detect particles. So one of the technical challenges is getting as cold as possible without unwanted nucleation as a background. So if it's like a bubble chamber, but in reverse, then colder should be better. Colder means lower energy threshold. So we want to avoid particulates that leads to something called heterogeneous nucleation. So for example, dust or impurities can create a false positive signal, can lead to freezing, to nucleation. There's also something called the homogeneous nucleation limit, where you go so cold that you can no longer sustain the metastable state. You also need to find the ideal rate of cooling. Too slow means too little lifetime, more opportunity from unwanted nucleation from vibration, background radiation. Too fast means you can introduce a thermal gradient, which also can could induce the unwanted nucleation. So we basically had a let's try it and see approach with the hypothesis that neutrons specifically could freeze supercooled water. So as I said, it had already been done for betas and gammas. Now you may wonder, so why neutrons? So the reason why is because neutrons produce nuclear recoil that we think dark matter would be able to produce. And so neutrons are the gold standard calibration source in dark matter experiments. So our prototype detector setup looked like this. A diagram here shows what's actually breaks down the different components of the experiment. So we had about 20 grams of purified water that was in a very smooth and cleaned, ultrasonically clean vessel assembled in a clean room. The water was processed The water was processed through multiple filters. It was deionized, ultimately distilled through a 20 nanometer flat sheet nonlinear membrane. So that's the last filter that the water sees right above the quartz vessel had 20 nanometer holes in it. So this is state-of-the-art nano purification technology in order to make the water as pure as possible. We had thermometers, thermocouple thermometers that monitored the temperature and look for the exothermic spike. So you can see the exothermic spike in real data that looks like the cartoon. So you can see that we were getting water as cold as negative 20 degrees at near atmospheric pressure. And a borescope camera that you can see here was used for image acquisition, only one. So we didn't have three-dimensional position information in the prototype, but we were able to, for example, count the number of snowballs produced by eye. We also had not pictured here, but beneath the quartz vessel, underneath the chiller, there was also a plastic scintillator with a silicone photomultiplier attached, and that was used as a coincidence counter, basically looking for flashes of light that were simultaneous with freezing inside the volume, which would indicate that radiation is freezing the water. So that as an additional evidence. So here are some images of the electron microscope images of the filter that was used for cleaning the water. And it has these 20 nanometer pores in it, which are not straight through holes though, but these cavernous pores. So this filter comes from Novamem, which is a company based in Switzerland that makes these nanoscale filters. So actually this is what we use for our prototype. This is no longer state of the art. Now you can get 5 nanometer filters that are even better. So we'll be able to purify the water to an even greater degree in the future. So detector operations were very, I say, MacGyver-like, if you've heard of that television show in the US in the 1980s. It means that, this is not a large-scale funded experiment like the Lux and LZ projects. We had to put this together, on the cheap with existing equipment in the laboratory as an initial proof of concept. So we were able to, even with very little equipment and funding, put together a prototype that could achieve negative 20 degrees Celsius at a cooling rate of minus 2 degrees per minute. So that's liquid water at negative 20 instead of 0. Or above instead of 0. This is nowhere near the coldest possible. But our goal was not being as cold as possible. In the prototype, it was just a proof of concept. To answer the question, can neutrons freeze water? We already know, as I said, from past data, that betas and gamma rays can freeze water under the right conditions, can freeze supercooled water. But we were asking a question, can neutrons do it? So, and that question would then lead to other questions of whether it could be done by dark matter or by neutrinos. But neutrons were our standard for the prototype. So we also had very little lifetime. So again, the focus was not building a perfect, beautiful experiment that then we can scale up to larger scales easily, but just an initial proof of concept. And so it took a very long time to collect data to melt water again after it had frozen. But we did manage still to explore multiple different run conditions to calibrate this. A control conditions, which is so no radioactive source, a 200 neutron per second americium beryllium source with and without lead shielding, and 10 microcurie, which is about 370,000 gammas per second, so relatively hot cesium-137 gamma ray source, and a very strong, the strongest source we could legally purchase without more, going up to, greater levels of permission is the 3,000 neutron per second Californium 252 source. And we use lead shielding on the neutron sources to block the gamma rays to determine whether it's neutrons or gammas that are doing the freezing, and also prevent gamma rays from affecting the thermometers. thermometer readings. So here are some example events. So at the left, we're going to go in order here, actually from the upper right. So we are long before we even had our nice negative 20 degrees Celsius prototype with the nice 20 nanometer filtration. Our initial tests were very, very simple. We're just in the freezer, literally in my office on campus. We took some water samples that weren't even this highly purified and managed to achieve a small degree of supercooling. So I'm going to play this video. I'm going to skip to the end though, where we start probing the water. Oh my God, that's awesome. Keep going, go to the bottom. That's liquid water at negative 8.1. Okay, shake it around. You did it! You did it! Awesome. It's frozen. Right. So you can see that we tested a sample of water that was in my freezer, and it was so well super cool that actually putting in the thermometer didn't immediately freeze it. We had to shake the thermometer around, and then you saw it formed into snow. So snow is a more appropriate term than ice, because with supercooling, you form more of a disordered crystalline structure. And so it's more like if you pour it out and play with it, it's more snow-like than it is like ice. So even if you fully degas, remove air and carbon dioxide from the water, you get a white instead of a clear freeze when the water freezes. So another example, so I'm going to actually change to a exit my PowerPoint for a moment and pull up another separate video that was just too big to embed directly into the PowerPoint slides. So here's our more advanced prototype. So this was down at negative 20 something degrees Celsius. So what you're looking at, this is the borescope camera, and this is the quartz vessel with 20 milliliters of water. So it's at negative 23 degrees Celsius. And there you go. So you can see there the water freezing, turning into snow. And you can see when it finishes freezing, the snow is in the shape of the vessel. So this is the hemispherical bottom and cylindrical shape of our glass test tube. So you can see it freezes into the shape of the vessel. So let me go back here to my PowerPoint presentation now. So here is an example of that same vessel you just saw in red. We just changed this is with the blue LED color illuminating the vessel. It was slightly easier to see the snowballs. This is an example of a triple nucleation event in the presence of a neutron source. So neutrons will rattle around in water. Since water is obviously rich in hydrogen, it can moderate neutrons, which have a centimeter scale mean free path in water, and you can get multiple nucleations within the same frame or from a different neutron in a later frame, and these snowballs then grow independently, merge together as they freeze the entire volume. And then we've continued to do more tests more recently, adding buffer liquids, different types of hydrophobic immiscible liquids, different types of oils on the top and the bottom to try to better isolate the water volume from the rest of the world, basically, to be able to do a better job in maintaining purification. So here is a more recent nucleation with some music added by one of my students, Josh Martin, from the television show Stranger Things, actually. So it's a little bit loud. I got to turn that volume down. There we go. I can kill the. Oh, I didn't mean to kill the music. I just wanted to make it softer. There we go. Yeah. So you can see the snowball formation there in real color. So I think that video was made on an iPhone, actually, on the student's iPhone. So you can see the beautiful snow formation there in the supercooled water. So, and here's another a slideshow with the red LEDs where you see a double snowball nucleation. So those are pretty pictures, but what are our quantitative results that we achieved? So we looked at the time the water spent supercooled, or more precisely, the time the water spent active. So at our high degree of purity, even radiation is not going to effectively trigger the water below approximately minus 16 degrees Celsius. So we look at the amount of seconds the samples spend below negative 16 down to their whatever final temperature before the nucleation occurs. And we compare the number of seconds spent active between all the different conditions we looked at and the minimum temperatures achieved. And what we found is that we, in the presence of neutron sources, the water would spend less time supercooled and freeze at a higher minimum temperature. And the statistical significance of the results varied from 2 or 3 to as high as 4.9 sigma for our Californium source, for our strong neutron source here, which on average was it would spend nearly a minute less time active or supercooled than the control data with no radioactive source. So the cesium, though, data was very interesting. The gamma ray data shows no statistically significant difference from control, which is the opposite of what was found 50 years ago and earlier. And we believe this is because there is a very, very sharp turn on of efficiency of sensitivity to gamma rays. And first, at the temperatures we were running at, you're first sensitive to neutrons. Before going colder, you activate greater sensitivity to gamma rays and to other forms of radiation. So it seems like you can tune this detector to have different sensitivity to different types of particles. One mystery, though, is that the effect seems to be enhanced with lead shielding. We believe this has to do with the alteration of the neutron's energy spectrum, but this is a little bit of a puzzle still. We do conclude, though, we still, despite these mysteries, we can conclude still with confidence based on the statistics of the data we do have in hand that neutrons can freeze water, which is the world's first observation of such an effect. As I said before, this has only been done with betas and with gamma rays by Varshnaya, but has never been done with neutrons as far as we know. We've checked the literature in condensed matter and in atmospheric science and chemistry, and we've never found a previous publication that shows neutrons freezing water. So this is the world's first evidence of that particular version of this phenomenon. And to make sure that this was a real effect, we alternated source and background runs and also checked room temperature as a possible systematic. Now, that's a table with numbers, but of course, as scientists, we like to see graphs are much more information, a better way of conveying information than tables. So you see here our various tests that we did, and the neutron sources are the ones that tend to are to the left of the control data in black. So this so in purple and red here is our ambi source. In red here is ambi again. Yellow is californium, and orange is what I called fiesta-ware beryllium. So that's actually a neutron source we created ourselves by taking a uranium paint coated dinner plate. So actually people, used to eat off this. So it's radioactive, but this is from a long time ago. The uranium paint was used to create bright orange plates called fiesta-ware still exists today. They don't use uranium paint anymore, certainly. But if you add beryllium to the fiesta-ware plate, you can create a neutron source. So we have americium, beryllium, californium, and our uranium, beryllium neutron sources we've created in order to test the device. But if you look at the in green, we have our gamma ray data from cesium is right on top of the control data. So at the exact conditions we ran our experiment, we do not see sensitivity to gammas, but to neutrons, which is actually exactly what we would want for a dark matter experiment that looks for nuclear recoil. We want sensitivity to nuclear recoil, but not to electron recoils. So as a check of systematics, this is the americium beryllium data in 2017 in the top row and 2018 in the bottom row. And across the three different thermometers, bottom, middle, top, middle, and bottom. And even though they all have variation, they all show the americium beryllium data to the left of the control. So showing that in the presence of the source, the water is supercooled for less time. So the californium data, though, with lead shielding was the most significant result, and it is offset in the greatest amount and the greatest statistical significance from the control data. Conservatively, though, we can look at the control data not from the entire year of data, but just the control data taken within days, alternating with the background data, the alternating californium and control. And while that's closer to the californium in gray, it is still offset by over 3 sigma of Gaussian difference in the peaks. And so on the left is the time spent supercooled, and on the right is the minimum temperature achieved in degrees Celsius, around minus 18 to 19. And in pink here is a comparison to simulation. So we were able to develop a simulation model that could replicate the californium data. So if we compare Jan4 simulations with the data, so Jan4 or G4, you may hear about it in other talks from speakers from different experiments like Atlas and CMS at the LHC. It's the software that's used to simulate one of the softwares that's used to simulate neutron, gamma, all kinds of, hadronic interactions. It's a piece of simulation software used in high energy physics. And we used it to determine if we place our ambi or californium source next to the water, what is the rate of interactions and what are their energies and where are they occurring in our 20 milliliters of water. And using Jan4, we're able to develop these spectra and see what is the spectrum of hydrogen recoils, oxygen recoils, and electron recoils for the different sources. And what we find is that the rate of proton and electron recoils are so large that in order to explain our data, it looks like that our device was only triggering on oxygen recoils. And the presence of the lead shielding modifies the oxygen recoil spectrum in such a way to put more oxygen recoils above threshold. So based on a comparison to simulation, we estimate that the nuclear recoil threshold was about 0.2 kV, except that after you add the effect of what's called the stopping power or DEDX threshold, the threshold in the density of the ionization produced, then the threshold is effectively about 1.2 kV for the oxygen recoils and for the hydrogen and electron as well. So it's not the lowest possible energy thresholds we can achieve with this technology, according to existing literature like Krovostianov and Curry from 2005. The energy threshold, this is in units of erg here, you convert this into KeV or EV. If we can go colder than minus 20 and achieve, for example, minus 30, we may be able to achieve energy thresholds of that are sub KeV, which is really great if you want to look for low mass dark matter particles. So digging deeper, though, into the californium to make absolutely certain that this is a real result and a real effect, we alternated. So we had 74 californium data points that were alternated with 85 control data points. And as you alternate, you can see the seesaw pattern as the minimum temperature achieved goes up when you add the californium, So you have Californium control, and the amount of time the water spends supercooled goes up in the presence of control, down in Californium, up again. So you can clearly see as we remove the Californium source and we put it back, how there is a very clear effect that the Californium is having on the water. We can look at the data also in 2 dimensions and plot temperature versus time, since the water is being cooled down at at approximately linear rate inside of our chiller, our cryogenic chamber. Although, calling it cryogenic isn't right. These temperatures, this is a cold day in Canada or Russia. No, it would be a warm day in Canada, actually, or Russia, -20. In Siberia, it actually be a good day. So this is not that cold, actually, which is one of the advantages of this technology. It does not have to be cooled very much in order to work. So we also did, in addition to the temperature analysis, we conducted an image analysis. And while we only had 1 camera, in the future we'll have multiple cameras so that we can do 3-dimensional position reconstruction. We were able to see by eye single and multiple scattering, and also different types of events like water surface and wall or bottom. In these images you see here, there's also, in the future, we'll have improved image quality. We have here glare from the LEDs in the bottom, so we'll fix that in the future with a more intelligently designed lighting system, and we also have glare from the LEDs in the water surface. So those are permanent features in all the images, but you can still see, despite that, those detriments to the image quality here in our prototype, you can clearly see single and multiple scattering. So actually, a blind analysis was performed where the students didn't know which folder was which folder was neutron data, which folder was control data, which folder was gamma data. And I had a large team of undergraduate students at the University of Albany scanning hundreds of thousands of images, because I did not trust a computer for the prototype. I wasn't going to trust this to like a machine learning or neural network thing. We will in the future, but for the prototype, I wanted human beings to make absolutely certain that this was a real effect. So after we finish the blind analysis of the images, we find a greater than 2.5 sigma significant difference between the control and neutron data. So the neutron data has a higher probability of multiple scattering. The gamma data is sort of in between. So the gamma data is inconclusive on the image analysis, but if we look at the temperature analysis, the gamma data is very conclusive that there is no effect from the gamma source. But the neutron source again has an effect in the image analysis, showing a significant increase in the number of multiple scatters. We even saw triple and quadruple snowball events, similarly to triple and quadruple bubble events in a bubble chamber, which uses superheating, the opposite of supercooling. We also had an enormous coincidence spike, so 0 here. So this is the difference in time between the moment of freeze as determined by the camera and these pulses that were in that coincidence counter I mentioned earlier. So we had a coincidence counter below the vessel where flashes of light, of scintillation in this plastic. So it's not liquid xenon, but similar idea as my talk from a week ago. This is just a little piece of plastic, though, that produces flashes of light when radiation interacts with it. And we can look at the difference in time between those scintillation pulses and the moment of freeze. And in the presence of the neutron source, you get this enormous peak where the neutron source and the moment of freeze are coincident. So coming back, though, full circle to what is the motivation behind this technology? It's the lack of discovery of dark matter as what's called the canonical WIMP, or weakly interacting massive particle, at a mass of 50 to 100 GeV. And so this is called the lamppost or streetlight effect, where we are looking for dark matter in the region where it's most interesting, where it's easiest, not necessarily most interesting, but where it's easiest to see at higher masses. So there's also this joke cartoon here of an astronomer and his spouse pointing out that he's missing the comet in his telescope. So we want to be careful that we're probing parameter space everywhere. Now, one of the reasons why we may not have discovered dark matter yet may be because it's lower in mass than we thought. So there's been an explosion recently, especially in the United States, of interest in lower masses, building experiments to look for lower mass dark matter. But in this lower mass region, the challenges are also different. The new so-called neutrino floor, where boron-8 and beryllium-7 neutrinos from the sun become an overwhelming background noise that makes it then hard to distinguish a dark matter signal from. So there are unique challenges in this low mass region. The biggest one, though, is how do you lower your energy threshold to be able to see these lower energy signals from these lower mass dark matter particle candidates. So the question we asked ourselves at my colleague Professor Levy and I at University at Albany is, what better target to look for low energy recoils than the lightest possible element, hydrogen? So obviously that's not the only idea. I have many colleagues who are working to get liquid xenon with me, but have competing ideas. There's helium, there's adding hydrogen to liquid xenon, for example. There are many other ideas, but the benefits of using water is that it's inexpensive and relatively easy to purify. So there have been very large-scale neutrino experiments at the multi-kiloton scale, like SNO in Canada, as Super K in Japan. So water is great at moderating neutrons, as well, as I mentioned, through multiple scattering. So it's inexpensive, easy to purify. It's great to tell the difference between neutrons and dark matter through multiple scattering. So it's a relatively cheap and scalable particle detection technology that has been used in the past already. So it has all of these great advantages. So what would be the potential sensitivity of water to dark matter? So on the left is what's called spin-independent dark matter scattering versus dark matter mass. So again, the further down the curve is, and the more to the left, the better. It means it's probing more possible parameter space. So the y-axis here, this is the cross-section, a measurement of the interaction probability of dark matter in square centimeters. So these are incredibly small numbers, again, 10 to the minus 34, 36, 38. And in yellow here, in yellow is the neutrino floor. So the neutrino floor is where it gets more difficult. Not impossible, but more difficult to look for dark matter, because if you build your experiment so big and run it for many years, you've become a neutrino detector. So neutrinos, as known from, this seminar series as part of the India-based neutrino observatory, neutrinos are interesting on their own, very important and interesting. But in a dark matter search, neutrinos are the bad guy because they can interfere with your dark matter signal by overwhelming your detector with too many neutrino events. So that's what these yellow regions represent. It represents regions where, again, it's not impossible, but it's more difficult to draw our curves here of sensitivity or limits into that region. And the left-hand plot is called spin-independent. The right-hand plot is spin-dependent. So we don't know what dark matter is. Is it a fermion? Is it a boson? What kind of spin does it have? So we can probe different types of interactions, and there are actually many more we can probe using effective field theory operators. So spin independent and dependent are just two very simplistic approximations of how we can break down our results. And spin dependent can be broken down into spin dependent proton, where the WIMP dark matter couples to the proton, or spin-dependent neutron. And this plot is spin-dependent proton. So first, let's look on the left at spin-independent. And you can see that the only that based on our projections here, really the main competing technology to water is helium. Helium is slightly more massive than hydrogen, but these are pure helium experiments, unlike water, and also have the potential to achieve perhaps lower energy threshold. Although water may be able to achieve comparable threshold, but that has not been demonstrated yet. So we have in light green, these are helium projections that are better than all the other. These are existing experiments and projections here. And in green are a couple different projections of what we can achieve with water. And this projection here in green is the more conservative one that uses only ideas that have already been demonstrated. And this would be only 1 kilogram, just 1 kilogram of water underground for just 1 year. But imagine what we can achieve with hundreds of kilograms in multiple years and with lower energy threshold, and that's what the dotted line is. And unlike other experiments, so the neutrino floor is less of a problem for water, and that's because it contains hydrogen. And actually, hydrogen has a lower neutrino interaction. The proton has a lower neutrino interaction probability as just being a lonely proton compared to helium and other elements. So a massive advantage of water is that this yellow region does not apply to water. It exists still for water, but it's lower than in these plots. And on the right-hand side, water is able to, at below 5 GeV in mass, there's pretty much no other detector technology that is able to probe this region of spin-dependent proton space. And that's because, again, of the hydrogen in the water. So the hydrogen is just lonely protons, and those lonely protons then can very effectively do a spin-dependent coupling to dark matter, but not to neutrinos. So there are technical challenges, though, certainly to achieve the projections in the last slide. We need to get what's called here capital J is the spontaneous nucleation rate. So in red is the bulk nucleation rate in number per liter per year, and in blue is the number of nucleations per square centimeter per year. This is a very aggressively log plot, so there are countless orders of magnitude that appear on this plot, and we need to live down here less than 1 event per year, because we want, in order to detect dark matter, we don't want false positives. We already have to contend potentially with neutrino backgrounds. We don't want spontaneous backgrounds from snowballs that just form spontaneously, not from external radiation. So according to existing data and literature on supercooled water, I have some references here. There are different models and contradictory data sets. So we cannot say this with certainty, but it does appear that there's a sweet spot somewhere between -20 and -40 degrees centigrade, where we may be able to achieve a very excellent experiment that does not have sensitivity does not spontaneously form snowballs too often, disrupting the experiment, creating false positives in the lifetime, but also still allowing for sensitivity to dark matter through a low energy threshold. So in our prototype, we did not get that cold. We only went to -20, but we are now advancing greater purification techniques, as I mentioned earlier, purifying now from 20 nanometers to 5 nanometers and using better materials to make our containers out of, using hydrophobic materials instead of quartz, to be able to basically reduce spontaneous nucleation on the walls, and the increased purity will reduce spontaneous nucleation in the bulk. So we already have some new data since our first paper, looking at, as a function of purity, basically the size of filter used, showing that we can achieve a lower temperature with a smaller filter size. So that sounds very obvious that this would be possible, but obviously we want to directly measure that in our own setup. And we already see evidence that, of course, a smaller filter will result in a lower temperature and thus in a lower energy threshold. So how do we optimize the energy threshold and also the DEDX threshold, the threshold in the amount of energy deposited per unit distance, which allows us to tell the difference between betas and gammas and alphas versus nuclear recoil from neutrons or hopefully dark matter. So actually in the last few months with the campus shut down due to the COVID-19 pandemic, actually I've built, I've moved the freezer that you saw earlier home just to my house, and have been, as the data comes in, sending it to one of our UAlbany students, George Homenides, who's been I just send him a zip file of the latest data to analyze how low in temperature we got, as you see here. So this is a very serious setup. It may not look, serious. It's tucked into the corner between clothes, but we may be able to continue taking serious, good data during the last few months. And we're exploring a multi-dimensional space to determine the best materials, the maximum volume, the maximum cool down rate, all these different variables, how much, what's the bath level we use, what's the external and internal containers we use, the shape of the vessel. We're trying to find what are the optimal conditions, not just the optimal temperature, but what are the vessel conditions that allow us to reach the lowest possible temperature, but not so low that we also have unwanted background. So it's a very intense optimization game across a multi-dimensional parameter space. So this has never been done before. Over the last, supercooled water has been studied for hundreds of years, and everyone has a piece of the puzzle. So it's just like the blind men looking at the elephant. Here we're trying to look at, with this very simple setup, we're trying to look at the entire elephant and not focus on only one aspect of supercooled water, but try to get the full picture of what is the optimal set of conditions that get us an experiment that will then allow us to scale up to a larger device. Because right now, of course, we're testing only a few milliliters still. So near future work with my colleague and collaborator, Professor Cecilia Levy, and her graduate student, Yujia Huang, who has been focused on position image analysis, image processing, better image processing, automated. We're not going to have, I'm not going to have 10 undergraduates look at hundreds of thousands of images by eye. Never again. In the future, we are looking to automated image analysis to be able to determine snowball position, first frame of appearance, number of scatters, growth rate, shape, etc., etc. There may be rich information such as directionality hiding in the snowball formation, as well as perhaps energy information or particle identification. So in the future, we will add more cameras and higher quality cameras with a greater number of frames per second to be able to probe the snowball formation with a higher degree of understanding. We're also going to, of course, try to lower the energy threshold, although we already have evidence of a very competitive threshold of order 1 keV, at least for oxygen recoils. We're not cold enough yet to see the hydrogen recoils, and that'll be a challenge, and we're relying on the hydrogen recoils for sensitivity to the lowest mass dark matter particle candidates. We want to do an optimization, as they said, of water volume, increasing the lifetime, which is one of the current biggest drawbacks of this technology. It's probably why the technology was abandoned in the 1970s. But nowadays, we have better technology to be able to potentially speed up the heating, the reheating of the device to melt the snow and reset the experiment. We may also be able to go modular. So it's possible that we'll never have a ton scale experiment that is one giant vat of water, but we may need to have a modular detector, just like Atlas or CMS at the LHC, or the Picasso experiment in Canada, now PICO, that had a modular detector. So there are, of course, drawbacks also to the modular approach, but that's why we're also exploring the ability to stay away from modules, have one very large experiment, and be able to stop the snowball formation, halt it, and reset more effectively. We're going to be doing more theoretical calculations and simulations in the future in order to have more extensive comparison to the neutron and gamma rates, and do an exhaustive characterization of energy, of the thresholds, not just versus temperature, but also pressure, and different kinds of different kinds of radioactive sources, different energies of neutrons. And the hardest step, of course, secure funding and start a global collaboration and program with this technology, especially if we can first show at the tabletop level the competitiveness on threshold. So in conclusion, we have not discovered dark matter. We have not learned anything new about neutrinos, but we've still made a discovery. It's not a major discovery, but we have shown that neutrons can make supercooled water freeze, and they can even multiply scatter as they do in a bubble chamber. At least some types of events are coincident with a scintillator, so we saw this enormous coincidence peak, and we have at least some degree of what's called discrimination between signal and background. So we have the ability to, it looks like, at least at the temperature and other conditions which we ran our experiment at, we were not sensitive to gamma rays, but only to neutrons. So we do not have a precision measurement of the energy threshold, but we have a lot of theoretical models and also data from other fields, not physics even, atmospheric science and chemistry, that suggests supercooled water must have an energy threshold well below 1 keV. We have, with a great error bar, though, we have determined that it should be about 1 keV already at minus 20 degrees Celsius in our preliminary data. And this technology has a tangential relation to other fields. So there's the cloud experiment, all capital letters, at CERN, which is being used to study cloud formation. So one of the secondary conclusions from our prototype, from our first experiment, is that radiation can cause supercooled water droplets in the atmosphere to freeze without the need for dust to begin the freezing process. So that has been a controversial. There's been back and forth looking at the literature in the atmospheric science field. There have been papers that say, yes, this is possible. No, it's impossible. And we believe we've resolved this contradiction. The reason why there was a contradiction is because depending on the exact temperature and potentially pressure as well, sometimes supercooled water is sensitive to some forms of radiation, but not others. So it may be sensitive, as we found, to neutrons, but not gammas. Sometimes it's sensitive to alpha, sometimes not. And that's not random. That has to do with both the energy threshold and the DEDX threshold, the beta block threshold. So all in all, though, this is a promising start to a rediscovered technology. As I said, I thought we had discovered it at UAlbany, but it turns out it was done, as I said, first in France, then there were theoretical papers in Russia in the 1960s, but then the major experimental work was done in India at the University of Roorkee in the late 60s, early 70s. So we've rediscovered this technology and improved it, shown a new feature of neutrons being able to freeze supercooled water. So with that, I'm going to thank, in addition, I said I have my close collaborator, Professor Levy. We also are building a collaboration with Brookhaven National Laboratory, Rensselaer Polytechnic Institute, Pennsylvania State University, and Duke University. So the research covered today was funded by the University of Albany, FRAP and PIFRS Awards, and startup funding for myself and Professor Levy. So with that, I will stop there, and we'll be very happy to take questions now.
Okay, so thanks, Matthew. That is very, very interesting work and very interesting talk as well. By now, we started actually enjoying your presentation and also putting up your slides so well and very appealing. As you really ended the talk by saying a promising start for a rediscovery of technology. Indeed, I mean, today it looked like a kind of little bit like a black magic, but I mean, the readout, the way you go ahead and analyze and look for it, but the fact that it could actually show, though some kind of, let's say, preliminary data, that this is a promising technology for, one of the technologies could be for looking at, as an important physics topics as dark matter and so on. So thank you very much. And now the talk is, of course, open for questions. We have, let me take one question right away from the YouTube participant. This is Dr. Harishri Krishnamurthy. She asks, can quasi-monoenergetic neutron sources be used for calibration?
Yes, so that's a great question. So a quasi-monoenergetic source would actually be better than what we have used so far. So we have so far used americium, beryllium, and californium, and that those sources, their advantage is that they're relatively inexpensive, easy to purchase and secure. So that's why they're common traditional sources, but they provide a spectrum of energies. It would be a quasi-monoenergetic source would actually be superior because then it would be easier to analyze the data and determine the energy threshold. So one of the things we're considering is we want to, what would be even better than a monoenergetic source is a tunable energy source, and that exists at Tunnel, the Triangle University's national laboratory, which is about a few hours a drive south from where I am in New York. So I've been talking with Professor Philip Barbeau, a member of who's on the faculty at Duke University, a member of Tunnel. So that's something we definitely want to do in the future as a way to more precisely calibrate this technology.
Okay, that's good. And we have another one from Abhinav Chaudhary. He asks that does dark matter may consist of more than one particle, and does dark forces also exist? Not clear to myself this question, but if you have figured it out.
Yes. So I personally, for years, I've been worried that our picture may be too simple, that dark matter is one thing and it's this or this or this or this. I am not a theoretical physicist, I'm an experimentalist. So my personal opinion is that dark matter is almost certainly going to be a rich dark sector of multiple particles with different interactions, with potentially dark forces, say their own interactions. To me, I find this very compelling because it could explain why we have not seen dark matter yet. Because maybe the problem is that yes, it's 25% of the universe, but what if that 25% is 5% this particle, 3% this other dark particle, and maybe it's not all one thing? And so that also emphasizes even more the need to have more experiments that are complementary, like this supercooled water, which doesn't, it's complementary to the liquid xenon experiments I work on. They don't compete. I'm not competing, with myself on these different experiments. These are different approaches that look for in different parameter spaces. So you're absolutely right that there may be numerous particles and multiple theories may all be correct. And it may be that we have a very rich sector, just like the standard model. I used to joke with my students all the time that there are alien scientists made of dark matter out there. And one brilliant alien scientist says, I have solved the missing 5% of the universe, and it's called the proton. They wouldn't be that far wrong because most matter is hydrogen, right? 75% of ordinary matter is baryonic matter is hydrogen, but they would miss everything, right? They would miss the rest of the standard model and the other quarks and leptons. And so I think it's possible dark matter may be mostly one thing, but maybe a collection of other things, a rich collection of other things.
That's very nice. And we still have a few more questions on the YouTube, but let me come back to Zoom, in which we have Professor Vivek Datar going to ask you a question or a comment.
Mm-hmm. I can't hear. So
Okay, I think he is not at.
Oh, sorry.
Yeah,
No,
here he
there we
is.
go.
Here he is.
Yes.
okay. Now I've unmuted it. Okay. When the water freezes, do you also get an acoustic signal?
Oh, we're not sure. Possibly, yes. We've been unable to see it yet because part of it is that the chilling mechanism is very loud. But theoretically, there should be an acoustic signal. You're right. So that's one of the things we're planning on investigating. We're going to use piezo electric acoustic sensors in the future because, as you know, unlike most liquids, water actually expands when it freezes instead of contracting. And so we are going to look for the acoustic signature because we're hoping that it'll be similar to the acoustic signature that experiments like PICO use for superheating, where the acoustic signature is different for different particles like alphas and neutrons. So it's possible not just that there's an acoustic signature, it's possible that that signature also contains information on the type of particle that interacted, like if we do a Fourier transform. We have not been able to do this yet, but we want to investigate that in the future.
Okay, nice. Thank you very much for a very nice, intriguing talk. Yeah.
Very nice one. Let us take one more question from Zoom. This is from Shailesh Pincha.
Hello.
Yeah, please go ahead.
Yeah, I have a question. I'm sorry if I missed the relevant explanation during the talk, but I was wondering, in that scintillation light pulses, the two pulses were of different widths. So were they like a random, or it depended on the time it took to freeze or something?
Oh, so no, that could be due to different types of particles interacted. So we have not investigated that more deeply. So in the scintillator, there are, even though the pulses are all designed to be the same height, there's different width. And sometimes the width has to do with multiple scattering. Also, you have indistinguishable multiple scatters in the scintillator. So what we do is and for this analysis, for the coincidence peak, we just take the rise the rise time of the left-hand edge, but we may be able to do more advanced analysis on the width. So we have not done that yet, but that is something to potentially investigate more deeply in the future. So it probably has to do with the type of particle as well as how many scatters interacted inside the plastic scintillator we were using.
Oh, okay. Thank you very much.
You're welcome.
So let us go back to YouTube for a couple of more questions. Again, once more, Arishri Krishnamurthy asking, has the relation between the gamma ray as an energy and freezing pattern been explored? In brackets, she says spatial or temporal. But that must be relatively easier than neutron sources.
Sorry, I couldn't hear the last sentence. Relatively easier than what?
Neutron sources. Should I read it again?
Yes, could you please repeat?
Yeah. See, the question is, has the relation between the gamma ray energy and freezing pattern been explored? Okay. And so, of course, he says spatial / temporal. And then that must be relatively easier than neutron sources, he says.
Ah, yes. So no, that has not been investigated, but on purpose, because so we were more interested in our prototype with neutron sources. Yes, it's more complicated, but we wanted to demonstrate whether we have sensitivity to nuclear recoils from neutrons as opposed to electron recoils from gammas. So if you look at this slide that I pulled up also, so at the temperature we were at, we estimate that we had about a DEDX threshold of about 100 MeV per centimeter, whereas the cesium gamma ray source would produce a DEDX from anywhere from 1 to 100, but not higher. And so we were not sensitive yet at negative 20 degrees Celsius to gamma rays. So we cannot do any energy, we cannot do any studies versus gamma ray, any energy or spatiotemporal dependence of like the snowball images or anything like that yet. In order to do that, we would have to lower the temperature. But according to our simulation, it looks like we were just very, very much on the border between no sensitivity to gamma rays to enormous sensitivity to gamma rays. So there seems to be a borderline that we are very, very close to. But in our prototype, we were on the side of the border, it seems, where we did not have any sensitivity. So if I go back, in fact, here, we look at the cesium-137 gamma ray source, we saw no effect from the gamma ray source, even though the gamma ray source was 2 orders of magnitude more gammas per second than either neutrons or gammas per second from the ambi or californium sources. And despite being a so much hotter, stronger source, even when you account for geometry and how many gammas reach the detector and their energies, there is absolutely no statistically significant difference between the gamma and control. And we believe that's because we were very slightly, very, very slightly too warm in order to detect gamma rays.
Okay. Another question, okay, it's again from Abhinav. It says, could dark matter have an electrical charge, and can ordinary particles decay into dark matter? Okay, so this is slightly different away from your actual experimental part, but I think I'm sure you can answer.
Yes, definitely. So yes, there are some models of dark matter. It cannot have a very strong electric charge, because if it did, then we would see evidence of, because, since the electromagnetic force is so many orders of magnitude stronger than the gravitational force, that even a small electric charge would create an enormously different cosmic structure compared to gravity, compared to gravitational forces. So there are models, though, where dark matter is milli-charged. So it's still quantized, but at a level much smaller than even quarks, than electrons or quarks. And in these models, dark matter would actually produce something. The dark matter candidate is called the LIP, lightly ionizing particle, where it could zip through a detector and produce a track of ionization, as opposed to the WIMP dark matter candidate, which just bumps into one nucleus and leaves. So to search for this kind of candidate, we're also considering this with the snowball chamber technology. And the idea would be, again, because I mentioned that sensitivity to gammas, similarly sensitivity for this type of electric or electron interaction, it would be possible if we went a little bit colder. And the idea is that instead of snowballs, we would see tracks of snow. And we know that this is possible because even though our experiment was not sensitive to gamma rays, was not quite cold enough yet, but the original work at University of Ruki in India by N.C. Varshnea, he showed tracks from gamma rays, actually. So the idea would be to look for tracks of snow instead of snowballs. But it's absolutely possible that dark matter has a small fractional charge. It cannot be, as I said, a very large electric charge, because that's been ruled out by cosmological observations. But there are models of dark matter where it's milli-charged. And so that is one of the possibilities that's on the table. And one of the things we are considering with this technology, even though that wasn't our primary focus, it is considered one of our secondary focuses.
Okay. Can I just ask you a clarification or question rather? In one of your last slides, you are also talking about possibly developing a kind of pixel kind of detector of the snow. You called that some SCCD or something.
Yes, I did. The supercooled droplet detector. Yes.
Yes. So can you say a word or two more on this?
Sure. So this is possibly necessary in order to solve the problem of lifetime. So the idea would be similar to the superheated droplet detector used by the Picasso experiment in Canada years ago. So the idea is that instead of having a large volume of water, to instead have droplets of water that are dispersed in a medium such as an oil an oil with that has a surfactant added to it in order to allow the oil and water to mix. So you basically suspend water droplets, liquid water droplets in an oil or in a gel of some kind. So not necessarily another liquid, but a solid. And what could happen then is you would look, visual would become very hard then if we're talking about microscopic droplets, but you might be able to use the acoustic signature mentioned earlier, and just like Picasso did. And the idea would be that when one droplet is triggered, it does not trigger the other droplets. So the advantage of the droplet approach would be you don't have the whole volume does not freeze when one droplet freezes. So that would be the advantage. The disadvantage is loss of these beautiful images of these large snowballs. But there may be a scientific advantage to going to droplets. So I hope that addresses your question.
Yeah, that's right. Yeah. Very nice. Okay. Okay. So once again, I think I don't see any more questions. So it's again my duty once again to thank you. In fact, thank you very much for coming back and giving this very nice, very nice novel detector. So one could even think of it's, as you very humbly put it, in as a promising start. But who knows? Maybe we will invite you again back after some days or some months or years, maybe making a major discovery using this concept and this detector. And we wish you all the best, you and your collaborators. Hopefully this detector will go places and do wonderful science. So on behalf of all the participants, once again, let me thank you, Matthew, both of the talks were really excellent. And so thanks once again. And I also would like to thank all the participants as well. And just before we leave, once again, let me remind you that we have the next talk coming up on Wednesday at 6 p.m. Where Professor Szydagis from Wisconsin is going to talk on triggering CMS physics on the high luminosity LHC in the high luminosity LHC environment. Okay, with that announcement, I would like to thank everyone to participate in this, and take care and stay safe. And let us see all each other again on Wednesday evening at 6. Thank you once again. Thank Matthew once again.
Thank you. Bye-bye.
Bye-bye. Thank you. Take care.